and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets and ventured to the edge of deep space. Where now?
Welcome, everybody, and thank you for coming. We're here today, closer to the stars than any other rooftop in America. My name is Yuri Milner. Last year, Professor Hawking and I, along with other colleagues, launched Breakthrough Initiatives, a program of research and innovation exploring the questions of life in the universe. But life in the universe does not only mean extraterrestrial life. It also means us. So today I want to ask a question and tell a story. The question is, can we reach the stars? Can we literally reach the stars? And can we do it in our lifetimes? The story is one of great leaps. About 75,000 years ago, humans crossed the Red Sea out of Africa. Since then, we have crossed every frontier on the planet. A few millennia ago, the Polynesians sailed into unknown seas. With no way of knowing what lay ahead, they risked everything and settled the Pacific. Navigating by the stars, they must have wondered what the stars really are. Then, a century ago, another great leap to the skies. And 55 years ago, this very day, Yuri Gagarin became the first human in space. My mother, who is here with us today, named me Yuri after him. Like so many others, I was inspired by his great leap, and I still am inspired. 8 years later came a giant leap. The moonshot was the climax of 7 long years of intensive research and development, and it cost in today's money over $100 billion. It was a scientific mission, but it measured something more, the scale of our ability and ambition. I believe it's time to test it again. The moon still marks the furthest point that human beings have come. Since then, we have delegated the job to our robots, some roving across planets, some roaming in space. And one of them, Voyager 1, has now reached interstellar space flying at 40,000 miles an hour. Is that as far as we can go? And what will be our next great leap? This is Alpha Centauri, our neighboring star. But in space, neighboring does not mean very near. Alpha Centauri is over 4 light years away. When we look at it today, we see it the way it was during the previous election cycle. 4 light years, by the way, is 25 trillion miles. That's 25 trillion miles. And the problem is, space travel, as we know it, is slow. If Voyager has left our planet when humans first left Africa, traveling at 11 miles a second, it would be arriving at Alpha Centauri just about now. So how do we go faster? And how do we go further? How do we make this next leap? The first serious proposal for interstellar flight was Project Orion. It was designed by one of the world's most renowned physicists, whom we're honored to have with us today, Freeman Dyson. Some versions of Orion would reach Alpha Centauri in less than half a century. And someday, human missions using fusion technology may indeed take us to the stars. But fusion was futuristic in the 60s, and unfortunately, it is still futuristic. As for the chemical fuel used in present-day rockets, that's a non-starter. To get a rocket to a fraction of light speed, a lot of fuel would be required. So much, in fact, that it would weigh about the same as all the stars in the Milky Way. But, ladies and gentlemen, there is a technology just over the horizon which can get us to the speed we need. Actually, we already use some of the basic principles. And it's very simple. Leave the fuel behind. Actually, Johannes Kepler was the first to take the concept of sails into space. In 1610, he wrote to Galileo saying, "With ships or sails built for heavenly winds, some will venture into that great vastness." It was another 3 centuries before scientists began to seriously study the concept of sailing in space. In 1924, Russian engineer Friedrich Sander even filed a patent using sunlight as a wind. Carl Sagan also believed that this idea was practical. And Andrew, and his partner in work and life, is also here with us today. Early proposals focused on sails driven by the sun. But it turns out that our own star, as big as it is, cannot produce the force required. For interstellar travel on human timescales, you need a much stronger wind and a significantly smaller boat. So how do we achieve this? Well, only in the last 15 years, 3 technological trends have made this possible. It was not possible before, but it is possible in the near future. And this is because of the exponential effects of the Moore's law. First, cell phone technology has sparked a dramatic decrease in the size of microelectronic components. From something like this to something like this. Its inventor, Zach Manchester, is here in the room. Zach, please stand up. Thank you. Zach is one of the members of our team. The one I'm holding is the first version with limited functionality, and there will be many more iterations to come. This is the star chip, a gram-scale wafer containing cameras, photon thrusters, power supply, and navigation and communication equipment. It's about the size of a large postage stamp, only a little bit thicker. This is the Silicon Valley approach to space flight, a fully functional space probe that can be held with 2 fingers and mass-produced at the cost of an iPhone. Our second breakthrough is the progress in nanotechnology, which is producing ever thinner and lighter metamaterials. This holds the promise of light sails a few meters wide, weighing just a few grams. Together, the star chip and the light sail give us an ultra-light, ultra-compact spacecraft. We call it the Nanocraft. This is the light sail, and this is the star chip, our Nanocraft, our interstellar sailboat. Now, so much for the sailboat. And what about the wind? Well, the third major development is in photonics, the technology of light. If I pointed this laser at a nanocraft in space, the light would actually push it. Not super fast. If I did it for a full day, it would push the nanocraft to about speed of an ant. But the advances in photonics had led the development of phased light beams, many small lasers forming one powerful beam. Philip Lubin, who is also with us today. Philip, can you please stand up? Philip has been thinking deeply for the last few years about how to use these latest developments to drive light sails, and we're also delighted to have him on our team. As lasers get cheaper and more powerful, in line with the Moore's law, the beam could potentially be scaled to something like 100 gigawatt level. In principle, the system should work like this. So this was the array. This is the mothership releasing the sail. This is, again, the beamer on the ground. This is the laser beam hitting the spaceship. The mothership releases the spaceship again. Another light beam pushes it second time. And of course, the idea is to have multiple redundancy and to send hundreds and maybe thousands of them to one target. Over a few minutes, this nanocraft accelerates to about 20% of the light speed. This is 100 million kilometers an hour, rather miles an hour. This is 1,000 times faster than the fastest spacecraft today, or 1,000,000 times faster than a car on a highway. At that speed, it would fly by Alpha Centauri about 20 years after launch. It could capture images of possible planets, other scientific data, and send them back home in a beam of light. The breakthrough Starshot concept is based on technology either already available or likely to be available in the near future. But as with any moonshot, there are major engineering challenges to solve. For over a year, our team has been working to identify and assess these challenges. The ones identified so far have been posted on our website along the potential solutions. And our advisory committee of renowned experts in the relevant fields has been supporting the efforts of our team. Breakthrough Starshot is based entirely on the work that is in the public domain. It is committed to full transparency and open access, pledging to publish all new results. We welcome the contributions of experts as well as public on our online forum. Breakthrough Starshot is a $100 million research and engineering program. It aims to demonstrate proof of concept of high-speed, light-driven nanocrafts and to lay the foundations for an eventual voyage to Alpha Centauri. The ultimate cost of such a venture is expected to compare with the biggest international science collaborations, such as CERN. When I was born, we were in the middle of a space race. But today, in 2016, here at One World Observatory, we are launching a collaborative planetary endeavor, One World, reaching out to the galaxy. And if this mission comes to fruition, it will tell us as much about ourselves as about Alpha Centauri. Only by challenging ourselves can we find out if we, like the pioneers before us, have the ability and ambition to succeed. For the first time in human history, we can do more than just gaze at the stars. We can actually reach them. It is time to launch the next great leap in the human history. And now I would like to introduce a man that I first met 30 years ago. It was at the physics conference. Back then, I was deeply affected by his qualities as a physicist and as a man. And in the years since, that impression has only deepened even further. It's a privilege to partner again with one of my greatest heroes and to launch this initiative. Ladies and gentlemen, Professor Stephen Hawking.
Good afternoon. We are here today to talk about breakthrough Starshot and our future in space. What makes human beings unique? There are many theories. Some say it's language or tools, others say it's logical reasoning. They obviously haven't met many humans. I believe what makes us unique is transcending our limits. Gravity pins us to the ground, but I just flew to America. I lost my voice, but I can still speak thanks to my voice synthesizer. How do we transcend these limits? With our minds and our machines. The limit that confronts us now is the great void between us and the stars. But now we can transcend it. With light beams, light sails, and the lightest spacecraft ever built, we can launch a mission to Alpha Centauri within a generation. Today, we commit to this next great leap into the cosmos. because we are human, and our nature is to fly.
I would now like to introduce our other speakers today. The first is Freeman Dyson. Obviously, we're honored to be joined by the world's most renowned physicist and mathematician. As well as being a pioneer of quantum electrodynamics, he is also one of the pioneers of the study of interstellar travel. Professor Dyson, please.
So, good morning, good afternoon. Thanks for inviting me here. We'll take a dissenting view about the aims of this program, because I've always believed that planets are not the big thing. I have a bet, in fact, which I made about 20 years ago, that when the first alien life is discovered, it will not be on a planet. Well, it remains to be seen, of course, whether that's true or not. But in any case, if you look at the universe from point of view of life, it's real estate which matters. It's the area in which life can flourish and support itself that is important. The area of grounds that is exposed to starlight or sunlight, where all kinds of creatures can grow. And if you look at area rather than mass, planets are not that important. Most of the area is, in fact, smaller objects, asteroids, comets, dust clouds, all kinds of small places which are much better for life. It has the huge advantage that it's easy to get off one object and move to another. You can hop into space, fly over to your neighbors, have a cup of tea and come back again, which is hard to do when you're on a planet. Anyhow, so I would say that if you look back at our history, there have been two quite different styles of exploring the planet Earth on which we live, which I call the Atlantic and the Pacific. The Atlantic style is Columbus, that is one entrepreneur deciding to make a big voyage to the other side of the ocean. And in his case, he thought he was traveling to China. He outfitted a big expedition with 3 ships paid for by the Queen of Spain, and the rest is history. He got not to China, but to America, and he got home again. That's the Atlantic style. Meanwhile, about 1,000 times earlier, the Polynesians had been doing the exploring on a very different style, which I call the Pacific style. The Polynesians, of course, had no intention of going to the other side of the ocean and coming back. All they wanted was to explore. They wanted to find out where there are places to live. And so they launched their boats on the Pacific and set out with pigs and chickens and bred fruit and other plants to sustain them and their children. And they just hopped from island to island and populated the Pacific over the course of 2,000 or 3,000 years. In my view, of course, both kinds of exploring will be important in the future, but I would say what we should do first is the Pacific style rather than the Atlantic style. That means, of course, looking to see what's there. Well, from the Kepler mission, we have learned that the galaxy is full of interesting objects, not just planets. We know that there are billions of planets. That has been the main discovery of the Kepler mission. But we also know there are probably trillions of comets and asteroids and smaller objects, which from point of view of life are much more significant. So that in fact, the space between here and Alpha Centauri is not empty, that it's not just a huge void which you have to cross in order to reach something interesting on the other side. On the contrary, there are thousands of objects in between. And in fact, we will be able to hop from one object to another much sooner than we could actually make a single big hop across the ocean. So my hope is that in the next 20 years or so, this venture which we're engaged on will produce the tools which will enable us to move forward. But we shouldn't say right away that we're going to Alpha Centauri. That's the same mistake that was made with the Apollo program, which was an Atlantic-style program, and it turned out to be a kind of a dead end for that reason. Once we got to the moon and got back, somehow the steam had gone out of it, and that turned out to be a dead end. Instead, there should have been a statement right at the beginning. This is a sustainable program which we're going to continue exploring. And that's what we are now engaged on. Thank you.
Yeah, I would definitely take Apollo as a failed project, but thank you, Freeman. So this is very helpful. And now I'd like to introduce Anne Druyan. Anne is a writer and producer of award-winning television, including the Cosmos series, and she's one of the creators of the Voyager Golden Record, the first and so far the only representative of human culture in interstellar space. Anne, please.
Carl Sagan was a very early proponent of solar sailing, although not as early as Friedrich Sonder. And I remember in the 1970s when he first described to me this means of moving through the cosmos. And I couldn't get over what a mythic achievement it seemed to me that it would be to be able to ride the light. What an immaculate way of traveling through the cosmos. And so a few years after Carl died, I became involved with the Planetary Society, working with Louis Friedman, who really wrote the textbook on solar sailing. And we had a suborbital launch failure in 2005, but we were working on a proof of concept mission. One thing we didn't think of doing was making the sail tiny, making the actual craft tiny. And I think that's the inspiring audacity of this mission. When I think of Jules Verne and his prophetic visions of the future, he always put heavy velvet curtains in his submarines with gas lights. And of course, we always make that same mistake. And when Yuri first told me of this mission, it reminded me in a very deeply moving way of the conceit that was at the heart of both Cosmos television series, and that is that Carl and I imagined human existence and human life as a kind of dandelion gone to seed in the cosmos, spreading throughout the galaxy and perhaps beyond. And here we have, thanks to these brilliant scientists and engineers, a real potential manifestation of that dream. I'm so proud to be associated with everyone here. And thank you so much for this time.
Next is Avi Loeb, chairman of the advisory committee of this project. He's a professor of science at Harvard University, where he serves as chair of the astronomy department, director of the Institute of Theory and Computation, and director of the Black Hole Institute. Avi, please.
So as all of us know, there is a big difference between exploring physically some other regions of space and looking at them from a distance. Columbus aimed at the Indies, the East Indies, but he found the New World. Starshot is aiming to image exoplanets near Alpha Centauri. We might find other things. And as a preliminary step, we will visit targets within the solar system. So moving at 20% of the speed of light, a small spacecraft will pass near Pluto within 3 days, rather than 9.5 years that it took New Horizons. Quite a difference. Another big difference is that one can send many small spacecrafts. Once a day, one can send hundreds of them a year, and one can sacrifice some of them. They can come very close to targets that we are interested in. For example, we are very curious about whether there is life on the moon of Saturn, Enceladus. There are plumes of gas coming off Enceladus, and one can imagine flying such a small spacecraft through the plumes and detecting molecules that might be indicative of life, fingerprints of life. But the bigger goal is to actually reach the nearest star, which is Alpha Centauri. It takes light 4 years to reach that star, or to reach from that star to us. And so we need to move pretty fast in order to get there within our lifetime. Roughly at 20% the speed of light, we will get there within 20 years. So the journey of such a small spacecraft, gram-scale spacecraft, starts with a launch that takes about 2 minutes, and then a 20 years journey to Alpha Centauri, and then the passage near a planet in that system, and a flyby that takes about an hour, during which the idea is to take images of the planet and send them back to Earth. There are many challenges in this project. It's an ambitious project, but we don't see any showstoppers, any deal breakers based on fundamental physics principles. So we think that we can overcome all these challenges with enough innovation and ingenuity. Basically, the success of this project depends on us. And we are calling for the help of experts in many aspects of this project from all countries. This is an international collaboration. We have an advisory board, but our goal is to get people all over the world involved, especially young people that will be around when we get there. Let me name a few of the challenges. One of them is the laser array. We need to produce a very powerful beam, laser beam, such that the force that it exerts on a sail would be strong enough. The beam will carry a power of order 100 gigawatt, that is similar to the power needed to lift off the space shuttle. And the launch will take about 2 minutes. In order to produce such a beam, we need to combine the beams of many small lasers, and that's a big challenge. We also need to prevent the atmosphere from blurring the spot of the laser beam. We need to produce a sail that is lightweight, attached to smart electronics that is also on the gram scale. That will require some work. And eventually, we need to communicate the image that is taken of a distant target to Earth and receive that image. On the way, there might be risks from impact by dust particles or the interstellar medium that we have to cope with. We have to shield the electronics against that. But as Oscar Wilde said, we are all in the gutter, but some of us are looking at the stars. Thank you.
Thank you, Avi. It is my pleasure to welcome to our panel Dr. Mae Jemison. Dr. Jemison leads the 100-year Starshot project, which maps out the vision for interstellar space travel. As well as being a former astronaut, she's a physician, engineer, professor, development worker, and a tech founder. Dr. Jemison, please.
Thank you very much. I want to just start off by recapping what we've heard. We've heard that collectively we as humans are at a point in which technologically there's at least one feasible path to getting to another star within our generation. And the other thing we heard is that there is a team that has the talent, the commitment, and the initiating resources to make it happen. But with all of those things there, how do we address what Freeman Dyson just asked about the sustainability? How do we do this in a sustainable way? I believe that we do it by understanding the purpose, the process, as well as the impact it has. First of all, with looking at purpose, let's think about things. An African proverb says, no one shows a child the sky. Going into space thinking about space exploration is as much a part of us as anything that we do. It is fundamental. Every group of people around the world have had astronomers, people who track the movement of the heavens. Space exploration did not begin with Sputnik. It began 1,000 generations ago when people started to understand how these stars, these lights moved around. So the purpose is part of what we do. The process is what we just started talking about, is it has to be collaborative. It has to bring in people from around the world. So as we start to look at this process, what will happen? Great and brilliant, talented engineers, scientists are not enough. We need the kinds of people or technicians who are well-trained superbly and who can work to put things together. That's not enough. We also need policymakers who can help to see past divisions that we think that are there. Those things have to happen. So when we look at this, the outreach is really about making sure that we understand some of the answers and the solutions are going to be found in other countries. They're going to be found by people who are graduate students. They're going to be found by people who we didn't even know were interested in this. And so we have to have those touch points to make things accessible. And then we have to look at education. Education is something that a 20-year program absolutely has to have. Those are things that we have to do. Those are part of the process. It is not closed, it is open. It is not about a single country beating another rival. It's about how we collectively, as humans, can do this, which brings us to the whole idea of impact. The impact of this, of course, will be the kind of technological achievements that have to occur. When you think about the technologies, we had that list of challenges that were there, including ones around policy and collaboration. But I mean, of course, we're going to learn about materials. We're going to learn about electronics, about miniaturization. We're going to learn how to communicate with very small instruments. We're going to learn how to make optics much smaller and get these incredible images and pictures. But the thing that we'll learn most, I believe, is creating a global ambition. How do we get everyone in this world to think about things better? How do we get an opportunity to see ourselves as Earthlings? Think about looking back at our solar system and knowing that not only are we there, but we're connected with the rest of the universe. And with that, I want to share with you the work that I do now, which is 100-Year Starship. It is about making sure that we have the capabilities for human travel beyond our solar system to another star within the next 100 years. This isn't about launching a mission. It's about ensuring an atmosphere that will allow us to seek bigger things. And so this Starshot is very much a part of that. How do we see ourselves as bigger? That's what we need to do. And my last piece is I want to share with you what I saw in space. When I was in space, I looked back down at this planet and I realized, yes, I belonged here. And then I thought about being 1,000 light years from here. And I realized that I belong there as well. You know, we are as much a part of this universe as any speck of stardust. That is part of us. And our destiny, yes, is to go there, but we have to do this in order to make life here on Earth better as well. Thank you.
Finally, I'd like to introduce Dr. Pete Worden. He's the executive director of Breakthrough Starshot project. He has been a professor of astronomy and is a world authority on space science. Among his many achievements at NASA, Pete is the former director of NASA Ames Research Center. Pete, please.
Good afternoon. Today is the day that space explorers have dreamed about. The stars are finally within our reach. But I wanted to first give you an update on the Breakthrough Listen initiative we announced last July 20th. It was designed to look for signals from an intelligent civilization in our galaxy and possibly beyond. This SETI search is orders of magnitude more encompassing and complete than any previous search. In addition, I'm going to give you a few perspectives on the benefits of Breakthrough Starshot. In January of this year, Breakthrough Listen began observations on the Green Bank Observatory 100-meter radio telescope. Now, this is the largest steered radio antenna in the world. We've already observed about 200 of the stars nearest to the Earth and 40 of the nearest galaxies. In the near future, we intend to observe all stars within 25 light years of the Earth and those stars within 250 light years that are similar to the Sun, over 1,700 stars. With the addition of the Australian Parkes radio telescope, the largest steered antenna in the southern hemisphere, later this year, we'll be able to observe the whole sky, including Alpha Centauri. We've also begun observations on the Lick Observatory Automated Planet Finder telescope. Now, with it, we look for optical, not radio signals, and this is particularly important because as Project Starshot is looking at, it will use lasers. These lasers could be detectable at very, very great distances. Indeed, a laser as powerful as we're talking about could be seen all the way across the universe. So one of the ways to find other civilizations that are doing the same thing we're planning on doing is look for laser signals. Now, most importantly, we're going to make all this available to the public, this data. Today, as we speak, much of it's going to be released through two means. One is on our website. The other is at the SETI at Home program, where you can actually download software and use your own computer to search for intelligent signals. Now, the technology implications for both Breakthrough Listen, that we started last year, and Breakthrough Starshot for people on Earth are really breathtaking. This technology will enable affordable, comprehensive exploration of our own solar system and the interstellar space near our Sun and all the way to Alpha Centauri, as Professor Dyson mentioned. This also will enable us to study the Moon, asteroids, and other objects in our solar system. But as we develop this beamed energy propulsion, it will also open up affordable ways to move things around our own solar system. This is the first new approach to propulsion really for a century since the liquid-fueled chemical rocket. And as I noted, it will give us the ability to travel around our solar system. Now, the light beamer itself has considerable potential as a science instrument in its own right. It can be used as a telescope rather than a light beamer, and it will be the most capable on Earth by over a factor of 1,000. It will be able to, for example, attack potentially threatening asteroids much deeper in space and obtain better astronomical data than ever before possible. Now, most important, I think, the breakthrough initiatives, both LISTEN and Starshot, will answer the fundamental science and human question: are we alone? We can search our galaxy and beyond for intelligent life, maybe even across the entire universe. And Project Starshot will enable us to see if there is any life near to our nearest stellar neighbors. And I just got to conclude by saying this is really cool. So through these hard challenges, on to the stars. Thank you.
Thank you. I would now like to open the floor for questions, but first I want to give a chance to Professor Hawking to answer the questions that have been submitted to him by some of the reporters over the course of the last few days. Given that he also attended opera and musical, he was only able to answer 7 of them. And we will try to go through them one by one. So the first question is, what could the development of new methods of propulsion mean for humankind's future in space?
Without new methods of propulsion, we simply cannot get very far. Not unless we are prepared to spend thousands of years in flight. Light-driven nanocraft are the most pragmatic technology available. Others, like fusion or antimatter, are a long way in the future.
In your estimation, what's the probability of finding intelligent alien life in the next 20 years and why?
The probability is low. but the discoveries of the Kepler mission suggest that there are billions of habitable planets in our galaxy alone. And there are at least 100 billion galaxies in the visible universe. So it seems likely that there are others out there.
If we find signs of intelligent alien life, what should we do next?
We should hope that they don't find us.
Why should humankind aspire to reach another star system?
Firstly, because there are no greater heights to aspire to than the stars. Secondly, it is unwise to keep all our eggs in one fragile basket. Life on Earth faces dangers from astronomical events like asteroids or supernovas, and other dangers from ourselves. If we are to survive as a species, we must ultimately spread to the stars.
Does we have any theories as to what intelligent life might look like?
Judging by the election campaign, definitely not like us.
What is Professor Hawking hoping to get out of this project?
Ultimately, a successful launch to Alpha Centauri within a generation.
What scientific finding of your life you're the most proud of?
I would like to be remembered for my work on Hawking radiation and the entropy of black holes.
So thank you. That finishes the answers that Professor Hawking submitted. Now we can open up the floor for questions to the group. Yes, please. Yeah, we have microphones.
Hello, I'm Hannah Thomas-Peter from Sky News. This is a question for you, Mr. Warden. Do you envisage this initiative cooperating closely with NASA, your former employer, and its experts? Have you already spoken to them about it? And what are your hopes for that collaboration?
Well, yes to the first two questions. We met with the NASA leadership last week and explained the program. They're very eager to support us. I might want to say, most important, the work that made this possible was funded by NASA. In fact, both Professor Lubin and Dr. Manchester's work was funded by NASA. NASA has a program called the NASA Innovative Concepts Program, Advanced Concepts Program. That funded this work. So we're very happy to work with NASA. We've also talked with the European Space Agency and other space agencies. So we're really trying to be inclusive. This is a global effort, so it should move forward in concert with everyone. So the answer is absolutely.
Yes, please.
Malcolm Ritter from the Associated Press. So is the whole point of Project Starshot to find life elsewhere? And if so, what kind of life are you looking for?
Well, Avi, yeah, you want
It's not the whole point. this is the first objective that we find most exciting. But like with any innovative project, there would be additional discoveries that will excite us in the coming decades. The challenge that we are facing is to move a small spacecraft to a very high speed and then pass by objects in the vicinity of the sun. And whatever these objects are doesn't matter for the objective that we have. And for example, if there would be a 9th planet discovered in the solar system, we could visit it, could pass by it. The advantage of small spacecrafts is that you can send many of them on a short time scale. And they do it pretty quickly. The NASA administrator changed between the time that New Horizons was launched and the time that it reached Pluto. If we send something at 20% the speed of light, it will be the same week that we will get there. So that's a great advantage, and you can imagine a lot of applications for it. I should mention that there are many benefits to life on Earth that could come out of the new technologies that we develop, just like with the Apollo program. For example, there would be advances in communication as we develop the techniques needed to communicate with the spacecraft, advances in optics of lasers, also advances in correcting for the atmosphere. Right now in astronomy, there is a method called adaptive optics, which corrects for the effects of turbulence in the atmosphere. But it's done on a scale of 10 meters, which is the scale of the biggest telescopes that we currently have. What we need for this project is the same technology applied to hundreds of meters to a kilometer scale. So up to 2 orders of magnitude, factor of 100, bigger optical system. And of course, there would be great benefits to astronomy, to science more generally. So the way to think of this is that when there is a vision for a grand project like this one, just like the vision that JFK had in the 60s, it lifts many boats. It makes people excited. It brings together the young generation to work towards an inspiring goal. And it basically makes us all very excited to be involved in this project.
Yes, please.
John Timmer, Ars Technica. It seems to me that the biggest challenge here is the energy budget required in getting information back from that distance. Do you have any ideas how you're going to power communication?
Maybe Pete, you want to take that?
Yes, we've looked at the end-to-end problem. That is one of the major challenges. But we expect to carry very, very small lasers on board the star chip. The sail itself, we believe, can be reconfigured as an optical element. So it's a 4-meter telescope. So we would use these very, very small lasers, which would have some fraction of a watt of power to send the signal back. We would then use the transmitting array. As I noted, can be used in reverse as a telescope, so that when you look at that, you can connect the link and perhaps get up to kilobits per second. But that is one of the big challenges. We'll have a number of intermediate steps and discoveries that'll get us there. But we are able to, at least in principle, show that with the things that we know today or can extrapolate, we could get back a reasonable number, a small number of images from the Alpha Centauri system.
The good news is that it will be easy to find the Earth from that distance because it's just next to the sun. Yeah.
Yes, please.
Seth Fletcher, Scientific American. What about the energy requirements for the transmitter laser itself?
Well, one of the things that we will have a small radioisotope source on board. It would be, in fact, most likely would be something like americium that are used in smoke detectors, and then a very small battery that would store that. This is within the margin or the mass margin, the weight margin that we've put together. But again, this is one of the challenges. But this one we think is fairly manageable.
Sorry, I'm talking about the beamformer itself here on Earth.
Oh, on Earth, and the interesting thing, although it's very, very high instantaneous power for a few minutes, the total amount of energy that's used is some small number of gigawatt hours. That's about the energy that a modest size chemical energy plant or a solar plant produces. What you would do is run a plant, say a 250 megawatt commercial plant, for a day, store that probably in batteries, although there are some new technologies like flywheels, and then would use that for a few minutes to fire. We would probably only fire once a day. So it's the energy source is not any different than a typical large power plant. Indeed, it's not too dissimilar to what the CERN system uses off the commercial grid. It's within a factor of 5.
Just to give the scale of the energy requirement, we need a power of about 100 gigawatt, that's the scale, over a few minutes. That's how much power is needed over the same amount of time to produce a liftoff of the space shuttle. So basically, we need the same amount of energy over the same time scale for this laser beam as you need to lift off the space shuttle.
I just want to show one slide that might answer some of the questions you might have. Next one. Next one. Next one.